Thanks. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this morning. And again, Lord, I thank you for these students. Pray you'd bless this class. Again, Lord, help us to glorify you in what we do this morning, Lord. In your name I pray. Amen. So you had a homework question? Which one?
It's number 19 and 9.5. It's not a very hard problem. Let's try to understand the process a little quickly.
So find the fundamental matrix for minus 1, let's see here. So we're supposed to find the fundamental matrix. What was it, number? Please, Tom? 19. So we've got x prime equals to ax, where a equals to minus 1, 1. 8, 1, and we're supposed to find the fundamental. I would say find a fundamental solution matrix. There are actually infinitely many of them, because we proved last time that if you take a fundamental solution matrix for a given system and you multiply by an invertible matrix, you get another fundamental solution matrix. So given that there are infinitely many invertible 2x2 matrices, that means there's infinitely many choices for your fundamental solution matrix. And that's why it says find a fundamental matrix, not the one. Okay. Of course, the matrix exponential is unique, right? But it didn't ask us for that, did it? All right, so what is a fundamental solution matrix? It is x equal to, let's say, x1, x2, right? With two things, right? First of all, x1 and x2 both solve the differential equation, and also we need that the determinant of x is not equal to 0. Right? These two things together give us a fundamental solution matrix. Now, if we can find eigensolutions, then we can construct x1 and x2 using our eigenvector technique, right? Okay, so let's do that if we can. The determinant of a minus lambda I is the determinant minus 1 minus lambda, 1, 8, 1 minus lambda. That's lambda plus 1 times lambda minus 1. I just distributed the minus, and then minus 8. Let's see here, what we got? We got lambda squared plus lambda, minus 1, minus 8. So altogether, minus 9. Of course, that factors, right? So this is lambda plus 3 times lambda minus 3. And so we can find the eigenvectors corresponding to those eigenvalues, right? So let's say lambda 1 equals to 3. We're trying to solve a minus 3i u1 equals to 0, which is what? Minus 4, 1, 8, minus 2, yeah? So what's this tell us u1 should be? So let's see here. I mean, we've got minus 4u plus v equals to 0. V is equal to 4u, if you like. So setting u equals to 1 provides what? V is 4. u1, the vector will be 1, 4 will do nicely, yeah? Of course, that we could have easily guessed, yeah?
So that's where my question sort of comes in. So looking for examples, are there multiple ways of doing this?
Yeah.
You plugged in lambda and set it equal to 0. But then in other examples, they take the original matrix and set it equal to u and v times lambda.
Right. Well, yeah, this is entirely equivalent to solving a u1 equal to 3 times u1. Like, that's the same equation. I just, and when I first did this course, some of the solutions, maybe you're looking at some of the solutions I wrote when I first did this course. I spent about before I ever taught this course, I just spent 3 weeks solving problems from the book. And over one summer, ages ago. But when I was first doing that, I was just solving it like that. But at some point, it dawned on me it's easier to solve equals to 0, especially once you've had linear algebra, because then that's a null space calculation, which is a standard calculation in linear algebra.
So one method isn't used in certain situations, they're interchangeable?
Yeah, yeah. And the thing about the setting equal to 0 is it allows us to use Gaussian elimination for more complicated examples. So it just feels like a good habit. The other way to think about it is, like I showed you guys last time, is really to get from here, right, to here. You could just by inspection look at the first column, first row rather, and see the second row is just twice, minus 2 times it, right? So if I can find a vector which is perpendicular to either one of these, we're good to go. So, 1, 4, flip the entries and put a minus on one of them. That's going to give us, a perpendicular vector. And if it's perpendicular to one of them, it's perpendicular to both of them, since they're scalar multiples of one another. But I don't know. You like that more? I mean, if somebody didn't show me this work here, right, I wouldn't think they cheated. I would just think they guessed. And once you write this down, you can make an educated guess to that. I think it's totally reasonable without writing work down, right? Now, there are some 3x3 examples we looked at last time, where if you just write down all possible solutions, I might be like, how do you do that? But not these ones. Okay, minus 3 then. Okay, well, finishing blow here. Therefore, this gives us one solution, x1 equals to e to the 3t, 1, 4, right? So there's one of my two solutions. And then lambda 2 equals to minus 3. We have a plus 3i. u2 equals to 0, which is really 2, 1, yeah? 8, 4. uv equal to 0. So by inspection, you can see u2 should be what? Yeah, 1, negative 2 will work nice. Therefore, x2, e to the minus 3t, 1 minus 2. And now we have everything we need to put together a fundamental solution matrix. X is x1, x2, and for the x's we just found, that will give us e to the 3t, 4 e to the 3t, e to the minus 3t, minus 2 e to the minus 3t. Now you might worry, is that matrix invertible or something? Well, the theory of linear algebra says that eigenvectors with distinct eigenvalues are pairwise linearly independent. So that pretty much frees us of that. Now, there's one thing I didn't tell you guys about, which is linear. Like, how do you judge linear independence of vector functions? I should actually talk about that for just a second. Then I'll take your next question. Linear independence of functions, vector functions. This will just take a second. So it's the same thing as before. We need that c1x1 plus c2x2 plus plus cnxn equals to 0 gives us what? If a linear combination is equal to 0, it must be that it's the trivial combination. In other words, that all the coefficients are 0. This is linear independence of a set of n vector valued functions, like we're looking at here. So how do you, if somebody gives you 3 vector valued functions, how do you judge if they're linearly independent? If they're right, if they're scalar multiples of each other, then they're not linear. They're linearly dependent, right? But this one's just kind of silly in the sense that so this is actually a function of time, right? This holds for all time, right? But for any time, you can rewrite this as the matrix equation: x1, x2, xn. Now, it was more complicated back in the case we were looking at scalar functions, because I actually had to take the condition and differentiate it n-fold times to obtain n equations and n unknowns. But here, one vector equation is already n equations, because these are n-dimensional vectors. Each one of these x sub i's, these are actually functions from like the reals to the n vectors. Yeah, these are vector-valued functions of a real variable. So the initial equation's already n equations and n unknowns if you just unwrap it into n scalar equations, and this is exactly, x times c equals to 0. And so to make sure that only c equals 0 is the solution, you can just say, okay, so if we have x inverse exists, right, that would tell me that c equals to 0. But, the condition that x inverse exists is the same, right, as if the determinant is non-zero. So we find that linear independence of x1 xn demands that the determinant of x1 xn be not equal to 0. Conversely, if the determinant's 0 for a particular time, for a set of solutions, it's the case that they're linearly dependent for all time. So basically the same theory we went over before goes through here with the caveat that the Wronskian, if you will, this is sort of the Wronskian. The Wronskian's just based on taking the functions and slapping them in a big matrix. There's no differentiation of functions. It's just the functions directly. So it's different, but it's the same. Anyway, I haven't emphasized this because it's not much to get into trouble with. Like the solution sets we find are linearly independent, so great. Like you can calculate the determinant of this. What is it? This times that gives me e to the 3t times e to the minus 3 times minus 2, also known as minus 2. And then I subtract the product of these two guys. Yeah, minus 2, minus 4, minus 6. Right. Is that non-zero? Yes. Okay. We're not working mod 6 or something, yeah? What's mod 6? I don't know. Strike that from the record. Yeah, so what was your other question?
When you first did the example, you had your lambda 1 was -3, lambda 2 was 3. So the order of the columns in your fundamental solution matrix, it doesn't matter what order they get fitted to?
No, exactly. If I had swapped the columns, then we would have found determinants. I mean, it does make a difference. I mean, the Wronskian would have been 6. The determinant of that matrix rather would have been 6 rather than minus 6 if I'd switched the order. So, I mean, putting minus 3 first also kind of has a time-honored tradition. A lot of times people list real eigenvalues in order of like increase, like from smallest to largest. That's a common nomenclature. The set of eigenvalues, by the way, is called the spectrum. And the reason for that goes back to the original application of these things to spectroscopy. The eigenvalues actually have to do with the energy of the systems that were studied. And so like if you put the list of eigenvalues like that, that's actually a list of the energies from smallest to largest for the problems they were studying. A lot of these things go back to, like the names for things go back to the application of linear algebra to quantum mechanics in the early 20th century. It wasn't so long ago that linear algebra wasn't a standard school course. It was research mathematics or physics. It wasn't that long ago. Although I think people have been solving systems of equations in school for a very long time. Like the Babylonians did it, I think. But not that all the Babylonians go to school, but then again, not all the Americans go to school either, right? Or Canadians. I don't know, are the Canadians here? Canadian! They're everywhere. Any Australians? There's sometimes Australians. You gotta watch out for them. Good actors, though. Let's see here. Any other questions? All right. So let's talk about energy analysis for a bit. Critical points, stability, all that jazz. This is partly chapter 5 and also sections 12.1 through 12.4 probably is where you might look in the book to see corresponding comments, all right? I mean, the story I tell is partly my own, so saying that would be good supplemental reading. I don't really get into chaos in here. I don't know enough about it to say things that are useful to you guys. So there's a couple pages on it in the book which are interesting, and there's whole other 1,000-page books written on it with lots of pretty pictures and stuff. It's a very popular topic. Yeah. All right, so here's the thing. Newton's equation. Newton's second law. Let's take the conservative case. So conservative case would be what? The net force is equal to minus du dx, where u is equal to the potential energy function. All right? So I'm thinking about a one-dimensional problem, and so if the net force is is conservative, then basically Newton's second law just says what? It says ma is equal to the net force, right? And that's minus du dx. All right. Let's see here. More to the point, what we have that m dv dt, right, is equal to the net force. Of course, what that really is m d squared x, let's say, dt squared equals to the net force, right? Now that's a second order differential equation. So if we're trying to visualize it in terms of the sort of pictures I was looking at the end of last class, that's not going to quite work for us, right? But we introduced something called the Poincare plane, where we look at position versus velocity, sometimes called the phase plane. And so what we do is use reduction of order to change this to a system of two first-order differential equations that have a lot of physical meaning, in the sense that we'll let x, let's see here. I mean, x1 is just x, and x2 will be v, right? So what's x1 prime? I like to use dots here, x1 dot. I mean, v is x dot, right? So x1 is just x2. Okay, that's not too bad, yeah? And what else do we have here? What's x2 dot? By Newton's second law, it's just the force divided by the mass, right? 1 over the mass times the net force. Because that's dv dt, it's the force over the mass. Does that make sense? So I mean, I can be more pedantic here. This is dx1 dt. This is dx2 dt. But, you know, now that I think about it, we could also just say this. We can say dx dt equals to v, and we can say that dv dt equals to what? One over m times the net force, right? Actually, does this assume conservative, what I've just done? If you look at this, I have not used that the net force is the derivative minus the derivative of potential energy function, have I? Not really, no. This, what I've just done, also makes sense for friction forces and other things. Provided the force just depends on position and velocity, we can still look at these differential equations and we can use p-plane and we could plot them, right, using that web tool or MATLAB. And we could study what the possible velocities and motions are for a given system using this idea, right? We'll do that. I just need to do a little bit more pen and paper stuff here before we get the computer out. But okay, so great. We could use p-plane to study these, right? Basically just thinking of v as being y, right? Because, the silly web tool I have doesn't give us the choice of naming our parameters, right? We've got x, we've got y, and we're kind of stuck with it, right? All right, whatever. I imagine if you use MATLAB in its full generality, it gives you the choice to name those whatever you want, if I had to guess. All right. So what are the critical points? For one thing, we could ask, what are the critical points of our system? So if I call this system of differential equations star, right? Now this isn't just any old system. This is a very special system, right? It's coming from Newton's second law. But for this system, what are the critical points going to look like? Aha. So they're where both velocity, right? V is equal to 0, and the net force is 0. These are critical points, where both the velocity and the force drops to 0. Now, but the net force is minus du dx, right? If it's conservative, again, go back to the conservative case here. I know I'm trying to have my cake and eat it too here, and that's bad, but I mean, this comment does not assume conservative yet, does it? No. These will be the critical points even for non-conservative systems, fine. If it's conservative, then we have the force is the minus derivative of potential energy, and so that being 0 means what? The derivative of the potential energy is 0, so if we have a conservative system, a critical point is a place where both the velocity is 0 and we have an ordinary critical point for the potential energy function in the sense of calculus 1, right? A place where we have a horizontal tangent for the potential energy. Or I suppose if you were dealing with a piecewise defined potential energy function, it could be a place where the derivative is not defined, you know? So ordinary critical point for potential energy as function of x. All right, so last time I also showed you guys the so-called phase plane equation. We looked at an autonomous system. What was an autonomous system? What we're doing right now is a special case of an autonomous system. So like an autonomous system, I'll remind you, we had that dx dt was some function of x and y, and we had that dy dt was some function of x and y, but not time, right? And I showed you, for these guys, we looked at some pictures. We looked at some of these. We'll look at more when I get the computer out. But I told you could take these two, and you can say, aha, well, dy dx, right? If you want to eliminate time and just look at the level curve, which the solutions to these parameterize, we can look at that as dy dt over dx dt, a la parametric calculus of calculus 2 in your education. Let's see here. And so dy dt, that's g of xy over f of xy, right? So we could solve this so-called phase plane equation and actually find level curves which are parameterized by the solutions to the system, right? So Newton's equation gives us a very special case of this. See, where the f is not just something random, it's very boring. It has to be basically equal to y, right? And the g, on the other hand, has to do with the net force divided by the mass. Same math. So we can look at the phase plane equation for our system here for star, right? So the phase plane, and what's its significance going to be? What's the phase plane equation for our system here, star? Let's see here. So we should look at d what? dv dx equals to what? So again, this is basically, look at that as dv dt over dx dt. What is that, though? dv dt is 1 over m times the net force. And dx dt, well, that's v again, right? So in Pfaffian form, the phase plane equation is v dv minus 1 over m, the net force, times dx equals to 0. So this is the phase plane equation for the reduced Newton's second law. Now, if it's conservative, we can do even better, right? I mean, like, if it's conservative, what is this? If f is a conservative force, what do we get then? We get v dv plus 1 over m du dx dx equal to 0, right? And if you multiply by m and just multiply by m, we get what? We get mv dv plus du dx dx equal to 0, right? Now, if u is just a function of x, what's du dx dx? U is just a function of x. This is just the total differential of u, right? That's just du. This is actually the differential of 1/2 mv squared, right? Because v is not a function of x. We take v and x to be independent variables. So in total, then, we've got the differential of 1/2 mv squared plus u equals to 0 for a conservative system. What is 1/2 mv squared plus u, though? Energy, right? You guys know this. So not surprisingly, we have just derived, and probably a way you haven't seen before. I don't think I've ever done it this way before. This is the first time I've ever done it this way. With you guys right now. You feel special? So the differential of the energy is 0, which means that energy, well, level curves of energy are the solutions to the phase plane equations. But they would be parameterized by the solutions to this second order differential equation in x, v, and independent variable time. So this is pretty neat. This means that this phase plane equation has special significance. Its solutions are curves of constant energy, which is a physically interesting thing, right? All right, so let me put it together here and show you an example for a specific physical system. Where should I work on it? Man, every bit here has something I want to keep. It's very annoying. We'll work over here. Sorry. Yeah, it's still a good zoom. It's fine. All right, so how about this? We'll think about the mass being 1, because mass not being 1, who cares? And we'll let the potential energy equal to, let's say, x times x minus 1. All right? If the potential energy is x times x minus 1, what does that mean the net force is? So the net force would be 1 minus 2x. What are the so what are the critical points then? Or I'm sorry, what is the critical point? There's just one critical point. So we'll have F net equals to 0 when x equals to what? 1/2? Yeah. So 1/2, thus 1/2 comma 0 is a critical point in the xv plane. The xv plane is also known as the Poincare plane, in honor of one of the mathematical physicists who first really showed the use of these ideas. Okay, so anyway, here's this example is not that interesting, actually. Sorry about that. So I'm going to draw up here. So here's the typical idea. We draw a potential energy plane, and then right under it, all right, right under it, we'll draw a xv plane. Because the shape of the potential energy function actually gives you a lot of information about the energy level curves. Their critical points are shared in some sense. All right, so like what's the graph of potential energy look like here? It's got zeros where? At 0, and let's say at 1. And it's got a minimum, right, at 1/2. So if you think about the potential energy, it's x squared minus x. That's a parabola which opens up, and it's got a vertex at 1/2. Nothing especially exciting there. Just that's what happened. So maybe it looks like that. This is a little bit qualitative, but there it is. All right, that's the potential energy. Now, so there is, of course, this at 1/2, something special happens, right? At 1/2, we have this critical point down here, right there, right? That's the critical point in the xv plane, 1/2, 0. And then what you can do is you can draw energy levels in the potential energy plane. And from those, you can extrapolate qualitatively what the solution curves have to look like. So, for example, this right here would be, let's say, E1. Now, this right here and this right here are basically as far as the particle can go with that energy. The reason for that is past here, right? This would be, corresponds to kinetic energy being less than 0 given total energy E1. See, the total energy is what? It's potential energy plus kinetic energy, right? So total energy in this case is, U plus 1/2 mv squared, right? In particular, for this one, that's x times x minus 1 plus 1/2 v squared for what it's worth, This is the energy as a function of position and velocity. It's a function of two variables. We're looking at what that green graph is, though, is potential energy, right? So if the red line is the total energy, right? If you're below the green graph, you have to have the sum of whatever the green graph value is plus kinetic energy equals total energy, right? So if you have to be above the green line, otherwise it would correspond to the kinetic energy being negative. Do you guys understand what I'm saying? So pragmatically speaking, what that means then is to figure out what the energy curve looks like in the xv plane, we just have to stay above the potential energy in the potential energy plot. So that corresponds to being stuck between, let's say, this x2 and x1 over here, right? So getting to the point finally, that E1 gives me something like that down here. And we can put arrows on it. The reason we can put arrows on it is what's dx dt? Dx dt is v, right? What does this say? It says that dx dt is positive when v is positive, right? Where is v positive in the xv plane? Above the x-axis, right? So the solutions have to flow right above the x-axis, and they have to flow left below the x-axis. When you think about an arbitrary autonomous system, there's all kinds of crazy stuff that could happen. Solutions can be flowing every different which way, every different place. But this is the Poincare plane. Position and velocity have a special and fixed meaning with respect to this equation. It forces the solutions to flow this way and that way in these plots. Another thing, the middle line, x equal to 1/2, this is where we have to have horizontal tangents for the energy level curves, because this is where what? This is where dv dt is 0, right? Which corresponds to only the x is varying. When both v and x are having derivatives which are 0, we're at the critical point. But otherwise, we have to have like a stack of horizontal tangents along that critical line. I'm telling you this because it's helpful when you think about drawing more complicated things. This one is relatively easy. Let's draw another one. So I introduced some terminology at the end of last class. You guys remember I talked about different kinds of critical points and, stable, unstable, all that fun stuff. So this critical point, what would its nature be? So here's E2, which I'll do in purple. That would give you another like this, right? I can't draw it very good. It's sad. You get the idea, even though my ellipse is not exactly flat where it's supposed to be flat. I mean, I'm trying to have horizontal tangent here, but not anywhere else as yet. Yeah. Ah. Spirit is willing, the pen is weak. Let's see here. Another energy level like this one here. So basically, it gives me another like that. And again, it's going that way, this way, and that way, this way. But you can, if you look at this, and you can explain the motion, right? How would you describe the motion for such a system? If you start out to the left, let's say, of x equals to a half, right? And you have a velocity which is right moving, what do? You go past a half, right? At some point you turn around and then you come back. And then at some point you turn around and you come back and you just keep going back and forth and back and forth. So if you look at the x, wherever you start, like if I start here, what's going to happen is that I go over to here, get to my maximum extent, and then I go back to my maximum extent, and then I go back. And then when I cross x equal to a half, I've got 0 velocity, right? The story I'm telling is a lot like a spring, isn't it? This is how spring works. It goes, oscillates as far as it can, swings back through its equilibrium position where it has what? Maximum velocity, rather. I said 0 velocity at the equilibrium position. That's nonsense. Through the equilibrium position, you have 0 potential energy, you have maximum kinetic energy, and that's the same story here. Like maximum kinetic energy as we cross the critical line, and then minimum kinetic energy as we get to the maximum position this way or the maximum position that way. This motion is bounded, and this is a stable critical point. Yeah. Of course, we could also solve this. We could actually find the energy level equation. I mean, we could actually solve this equation here without a lot of trouble, right? Maybe it's worth doing that. The point of this really isn't that we can solve equations, though. The point of this is that we can analyze Newton's law qualitatively using this phase plane idea. So there's lots of forces I could write down that I might not be able to find a closed form solution for them, like actually integrate that equation, and yet I can plot the force velocity curves and study the motion. Let's see here. So let me just write down what was my equation I'd have to solve? Was it, sorry, I'm trying to stick with what I've developed here. So we'd have to solve VdV minus, I mean, it's kind of dumb when I write it down, you'll see. The net force, what was it? 1 minus 2x. Was it plus the net force or I can't? Minus the net force, yeah. So minus that dx equals to 0. So what's the solution to this differential equation? So I have 1/2 v squared, right? And minus x plus x squared equals to a constant. Let me call that constant e. That's not surprising. That's the potential energy, which is x squared minus x plus the kinetic energy. Those are the solutions to the phase plane equation here, because they're energy level curves. Then the thing is, this, right? Maybe it's not immediately obvious that these are ovals to you, but that's x. That's x. This is actually x minus 1/2 squared, right? Plus 1/2 v squared equals to what? E plus what? E plus 1/4, completing the square. So as you can see, we have ovals in the xv plane. And these ovals are energy level curves. Here, let's do another one that's free me of the obligation to give you a formula for the potential energy. Let me give you a potential energy graph. And sometimes it might be the situation that you have some experiment where your experiment uncovers what the potential energy graph must look like, and yet you don't have a formula for it. Like, that's possible. Here we go. Suppose my potential energy looks something like that. Potential energy, x, and I want to plot down here, attempt anyway, to plot some energy level curves. All right, so we need to kind of draw some sort of common points here. And I try to draw them right on top of each other so I can just drop some points of reference, like here's x1, let's say. And the other critical energy, critical number here would be x2. Is there any other? Oh, here's another. So places where you have a horizontal tangent for potential energy are places where the net force for the conservative system would be 0, right? These would be critical points for the system. I think that's enough. All right. So it goes on and on, it goes on and on, right? So this problem has 3 critical points, right? So the critical points, of course, on the potential energy graph are here, here, and here, right? The critical points in the Poincare plane and the xv plane are down here. This guy, and this guy. And usually the question I would ask would be something like this. Given this potential energy diagram, plot the Poincare plane, plot the position versus velocity plane with at least 5 interesting energy levels. And if I know what's good for me, I will tell you which energy levels. You know, I might say for energy E1, E2, you know, E3, E4, and E5, something like that. So energy 1, I think actually, let's see here. Actually, I should put E2 like here. I want E2 to be that energy. Okay. And I wanted E3 to be this energy, right? And I guess I want E4 to be this. I'm sorry, guys. E4 to be that energy. These are, but I really need a couple more because these are too special. I need like, stink. Let's just start with E1 and I'll add a few more to help as we get going, all right? E1. Here. So if we look at this, I'm drawing dotted lines because this is classically forbidden. The dotted line is where the net energy is less than the potential energy. That means kinetic energy is negative where I have this dotted line. Now the solid line here and here are classically allowed. These are regions with with positive kinetic energy. And so dropping that down here and here, basically we just get these kind of deals. Where it's coming in like that, it gets to that point, and then it goes back out again. Here, it's to the left and to the right. So there's E1. Not especially exciting, but there it is. So is it possible to have energy E1 and be between these 2 points? Like, no, you can't have energy E1 and be closer to the origin than these 2 critical points here. I mean, these are points of closest approach to the origin for energy E1. How about E2? I'll do that one in red. So here, E2, here's where it's allowed. Is no allowed. There's a point where it's allowed, and then it's allowed again over here. So dropping that down here, here. We get just that critical point right here, E2. It's lonesome, and then like this again. It might be helpful for me to put in like put E6 here. Let me put E6 between E2 and E3, and I'll make it wiggly. Wiggly-doo-doo-doo. So E6 would be something like this. So there, E6, you'd have like a little, let me not make it wiggly, I'm sorry guys. It's stupid. But it would give you a little stable oval around here, up to the limits of my artistry. That's here. And then, of course, you also have, it comes a little bit closer at here. You guys follow me? All right, E3. Let me do that one in blue. So E3 is classically allowed out here. It's forbidden there. You got another one's allowed here, and then out to there. So here's my E3. So basically we have a point of closest approach, like here. Right. Down here, something like this. So here we have kind of like a fish. So if you're close enough to the critical point with energy level E2, right, at x2, you've got these stable elliptical orbits around that point, you know? Your motion's going to be bounded. But if your energy gets too big, what happens? You escape off to positive infinity, right? If your energy gets too big, if your energy gets bigger than E3, then you can kind of get up over this potential well and just keep going and going and going, right? I'm going to include an E7. I think it's helpful. I'm going to put E7 right here between what I called E4 and E3. Classically forbidden. And here we go, E7. So it gets a little bit closer there. It doesn't have a critical point. So it's like what happens here then. See, it still should have sort of like horizontal tangent as it crosses this point. And over here it should drop down. It has, again, it has a horizontal tangent as it crosses that critical line. And then it'll bow back up and go on like that. So it's kind of a modified fishy, if you allow me to use a technical term. So here, E7. And, okay, so like, yeah, one of these guys. I'm doing my best, but you should understand that this is a qualitative picture, right? It's not quantitative. But it does have a lot of useful, and as much as this is a qualitative picture, it does have quantitative information in some sense, right? I mean, like, it says definite things about how the motion is in different sectors. But it is qualitative in the sense that I can't get precise numerical, I don't know, you have to do some algebra to figure out what x1 and x2 and x3 is for a given function or something, right? All right, finally, let's get to E4. Let me make that one, I'll use the pink marker. For E4, up here, right? So it's something like this guy, modified fishy, out to infinity. Roughly speaking. Here's our E4. It's going through this critical point at x1, like that. right? And then finally E5, just to finish it. Up here, this has, if you have energy E5, your motion's not bounded, right? If you start out moving left, if you start out moving right, I guess it depends on which right or left we're talking about. Anyway, if you're moving this way to start with, and you have energy level E5, you just keep moving that way forever and ever. You slow down a little bit in certain places, but you stay going that direction, right? If you have energy level E5 and you're going to the left, you keep going to the left for all time. You might slow down when you get close to the critical energies, critical points, but that's it. So there's two disconnected so basically horizontal tangent, horizontal tangent, horizontal tangent, and then, I can't do it very good, but this is what E5 looks like, right? And then down here, so the larger the energy gets, the less dramatic these slowings become, right? But the two black lines, these are disconnected. There's no turning back if you have energy level E5. For other lower energy levels, depending on where you start, you may end up somewhere different, right? So a good question to ask for these kind of problems is the motion bounded? The motion is bounded here in some cases, but not in others. The motion for energy level E5 is unbounded in all cases. It doesn't matter where you start. For energy level E6, the wiggly one, depending on where you start, your motion may be bounded or unbounded. E6, if I start here, the motion's unbounded because either I'm going to the left and I just keep going, or I'm going to the right, I hit the potential well and I bounce back. So for E6, the motion's unbounded if I start here. On the other hand, for E6, if I start right here, the motion's bounded between whatever I want to call these, x4 and x5, right? If I start with energy level E6 right there, I'm going to have an oscillatory motion between x4 and x5, so the motion's bounded, given that starting point. On the other hand, if I have energy level E6 and I'm given this starting point, the motion's unbounded again, because either I'm going to keep going to the right forever and ever, or I'm going to be going to the left, I hit the potential while I bounce back, and go on and on. So this, guys, is what I mean by energy analysis, right? I keep using the word classically. Do you know why that is? Because in quantum mechanics, you learn about something called tunneling. And tunneling allows you to do stuff like you can still have particles. You can have particles with, in some sense, negative kinetic energy over a small distance or something. This is allowed for, and it allows for these weird things you've heard about, like quantum mechanically, there's some very small chance that you could actually walk through a wall. Like classically, this is forbidden, but quantum mechanically, you can, these rigid energy considerations are muted a little bit by the phenomena of tunneling. And it's not just some sort of like, no one's, as far as I know, people don't walk through walls. Right? It's pretty rare. I've seen some movies about people like half walking through ship's decks and stuff. You ever seen the Philadelphia Experiment? You ever seen this? Nah, right. Ancient sci-fi movie no one cares about. But other things, tunneling is actually important, like semiconductor devices, things we build computers from. The phenomena of tunneling is a central thing that's important to understanding the way modern electronics work, actually. It's something we use in the construction of physical devices. It's not just a weirdo, oddball case. All right. I think we'll take a 10-minute break. When we come back, I'll do some stuff on the computer to illustrate this further. Thanks, guys. We'll start again at noon.